The maximum a posteriori criterion is the optimal design criterion for a detector. It's the criterion that minimizes the probability of error. When all the symbols are transmitted with the same probability, the maximum a posteriori criterion becomes the maximum likelihood criterion. The posterior probability of a symbol is proportional to the product between the probability of transmitting this symbol and the conditional probability of the observation given this symbol. Because of this, the maximum a posteriori criterion says that a given value of the observation space Q is assigned to the decision region of the symbol having the maximum posterior probability, of the symbol having the maximum value of the product between the probability of transmitting this symbol and the conditional probability of the observation given this symbol. If all the symbols are transmitted with the same probability, we can remove in the comparison the probabilities of transmitting these symbols. And in this case, for equiprobable symbols, we have the maximum likelihood criterion. In this case, a value of the observation space is assigned to the decision region of the symbol that maximizes the conditional probability of the observation given the transmitted symbol. This is the maximum likelihood criterion. In the common case of Gaussian distributions, for these conditional distributions of the observation given the symbols, the conditional distribution for symbol AI is a Gaussian with mean AI, the maximum likelihood criterion can be understood as follows. We compare these conditional probabilities, and in this example, in a one-dimensional space, the threshold is just in the middle between the two symbols, the middle between the two Gaussian distributions, because this point here where we have that both conditional distributions are equal is the point in the middle between A0 and A1 in this case. The probability of error in this case is the average, 1/2 and 1/2, of the integrals of the conditional distribution of each symbol in the decision region of the other one, because when we transmit A0, an error will happen if the observation is in the decision region of A1. And similarly, if we transmit A1, an error will happen if the observation is in the decision region for A0. Therefore, the probability of error is the average of the two areas that we have here in blue and in red. Taking this into account, we can see that the optimal threshold defining the decision regions is QU, the middle point between A0 and A1, because if we modify this threshold, some area here or here will be added in the computation of this probability of error. Therefore, this is the optimal threshold. This is the best threshold for a situation like this one. With equiprobable symbols, the decision regions are obtained by comparing the conditional distribution of the observations given the symbols. And if these conditional distributions are Gaussians, like in this example, it is visually very simple to see that the decision region for a symbol, for instance for A0, are those points in the observation space closer to A0 than to A1, and the decision region for A1 are those points in the observation space closer to A1 than to A0. This, that can be seen easily in this particular example, can be analyzed mathematically. And when we have equiprobable symbols and Gaussian conditional distributions for the observation given the transmitted symbol, the comparison is just between these two Gaussians in general, or more than one Gaussian in a in a system with a higher number of symbols, but this term and this term can be removed. In the comparison, then the same thing happens here and here with the complex exponentials. The exponential is a monotonic increasing function. This means that we can remove the exponentials, and with the negative sign we can modify the sense of the inequality, and basically the result that we have is that the maximum likelihood criterion with Gaussian conditional distribution becomes the minimum Euclidean distance criterion. An observation Q0 is assigned to the decision region where the distance with the symbol is lower than the distance to any other symbol in the constellation. Here we talk about distances because the norm of a given of the difference between two vectors is equal to the distance between vectors. Here, in fact, we have the comparison of square distances, but the square is a monotonic function, so the criterion can be explained in terms of the distances of the observations with the different symbols in the constellation. And a given observation is assigned to the decision region of the symbol that is closer to this observation. This is the minimum Euclidean distance detector that can be applied for equiprobable symbols and Gaussian distributions. Actually, it can also be used for any symmetric conditional distribution, because if the distribution is symmetric, the thresholds will intersect in the middle point between two symbols. And here we have a block diagram illustrating this decision criterion. The observation is compared with any symbol in the constellation, and the decision is the symbol at minimum distance of the observation.